Consider the plane curve defined by the parametric equation x of t and y of t. Suppose that derivative of x and derivative of y with respect to t exist, and assume that derivative of x in terms of t is not 0, then the derivative dy dx is given by dy dx equal dy dt divided by dx dt. Now take a look at the proof. Let y equal f of x, and then y of t is equal to f of x of t. So when we take derivative both sides, we have to use the chain rule. So then we have f prime of x of t equal y prime of t divided by x prime of t equal dy dx. Find the equation of the tangent line to the curve x equals secant of t and y equal tangent of t in the interval from negative pi over 2 to pi over 2. At the point square root of 2, 1, where t equal pi over 4. So first we need to find the slope of the curve, right? We need to figure out the slope of the tangent line. To find the slope of the tangent line, we take the first derivative, dy dx is equal to dy dt divided by dx dt. Derivative of tangent of t equal to secant tangent. Derivative of tangent equal to secant squared of t. Derivative of secant equal to secant of t times tangent of t. Simplify this, we get secant of t divided by tangent of t. We will evaluate this derivative at pi over 4. So we get this equal to square root of 2. Now that we have the slope of the tangent line, we can use the point slope formula to find the equation of the tangent line. And this equal to, so that is the equation of the tangent line to the parametric curve. Let's repeat this with the next one. Find the equation of the tangent line to the curve defined by the equation that x equal to t squared minus 4t and y equal to 2t cubed minus 6t for t between negative 2 and 10 when at t equal to 5. Okay. So again, let's go ahead and find the slope of the tangent line, dy dt equals 6t squared minus 6 divided by, this is dy dx, divided by 2t minus 4. We will evaluate this at t equal 5 and we get 24. Well, we can calculate the value, the point xy when t equal 5. So when t equal 5, x equal 5 squared minus 4 times 5, this is 5. Y equal 2 times 5 cubed minus 6 times 5, and that is 220. But I can write the equation of the tangent line, y minus 220 equal 24 times x minus 5. So y equal 24x minus 120 plus 220. Excuse me, this should be 120, right? So this is 2 times 125 minus 30. Yeah, this is 220. So then y equal 24x plus 100. So that is the equation of the tangent line to that parametric curve. Now, we talk about the first derivative. We can still take the second derivative. So how do we find the second derivative of parametric equation? We first would take the first derivative, then the second derivative is given by the formulas d dt of dy dx over dx dt. So how do we apply that? So let's go ahead and try our first problem. Find the second derivative as the function of t if x is equal to t minus t squared and y equal t minus t cubed. So let's first calculate dy dx. dy dx is equal to 1 minus 3t squared divided by 1 minus 2t. So then d dx of dy dx is equal to d dt of dy dx divided by dx dt. So d dt of dy dx, we take the derivative of 1 minus 3t squared divided by 1 minus 2t. So we use quotient rule. Divide by dx dt. So clean this up. Okay, you can simplify this further. To get 2 minus 6t plus 6t squared divided by 1 minus 2t cubed. Now, just like graphing a curve, well, we're interested in knowing what is the area under the curve, what is the volume, what is the arc length. So let's take a look at the area under the parametric curve. Consider the non-self-intersection plane curve defined by the parametric equation x equal to xt, y equal to y of t, where t is varied between a to b, and assume that x of t is differentiable. Then the area under the curve is given by area equal to integral from a to b to y of t times x prime of t dt. Let's find the area enclosed by the asteroid. X equal cosine cube t and y equal cosine cube t. For t is between 0 to 2 pi. Now, this is the asteroid, so the if I get the graph of this, it looks like this here, and it's between 1, 1. So this is the curve, what it looks like, and it's symmetric. So that's the case, I can calculate the area of this one piece, then multiply it by 4 to get the area under the curve of the whole thing. So I can go ahead and calculate the area as follows. The area is calculated from 0 to 1, from 0 to pi over 4. No, pi over 2, because we split the circle into 4 pieces. Okay. Y of t equals sine cubed of t. X prime of t is 3 sine squared t dt. Cosine squared of t dt. And here we have a chain rule, so another sine t. There we go. Let's simplify this. We get 4 from 0 to pi over 2. The sine to the 4t. And we have a 3, so bring that down. Here's 12. Cosine squared of t dt. I can lower the exponent. So 12 from 0 to pi over 2. The 1 minus cosine 2t divided by 2 square times 1 plus cosine 2t divided by 2 dt. Now we have 3/4 0 pi over 2 of 1 minus cosine 2t minus cosine squared of 2t plus cosine cubed of 2t dt. Evaluate this at pi over 2 and do this integral. We can use split this apart. We can evaluate each of those integrals and calculate and evaluate at from 0 to pi over 2. This sum up to 3 pi over 8. That is the area under the parametric curve.